Hello everyone, welcome to this video wherein I will be talking about the answers to your semifinal exam. Hopefully this will serve as sort of a review to your upcoming final exam, which is a comprehensive exam. We will go through all of the items here. We'll start with the first part, which is a multiple choice. Number 1 reads, which of the following statement about carboxylic acids is true? You're given here 4 choices. Carboxylic acids are less soluble in water than alcohols. Letter B, have higher boiling points than aldehydes and ketones. Letter C, are less polar than alcohols. Letter D, are more soluble in nonpolar solvents than aldehydes and ketones. So for this item, you're actually being asked regarding the polarity of your carboxylic acid functional group. Remember that the structure of your carboxylic acid group, we'll draw it here, C double bond O, O, H. Okay, so you have this bond here, your C double bond O, the carbonyl group, that is a very polar bond. And then you have this bond here, C single bond O, that is another polar bond. And then you have the third one here, this OH. This is a very polar bond as well. So you have actually 3 polar bonds within the carboxylic acid functional group. In fact, your carboxylic acid group among all the functional group is the most polar out of all. So if we're going to compare the functional groups, we'll start with the alcohols. Your alcohols, OH, is polar, then followed by your aldehydes and ketones. Your aldehydes and ketones are relatively within the same ballpark in terms of polarity. And then you have the carboxylic acids, which is the most polar out of all the functional groups. Of course, alkenes and alkynes are not in question because those are non-polar functional groups. So that would give us that will actually result in the properties of your carboxylic acids. Namely, if you have a more polar functional group, that is going to result in a higher boiling point, and then also a high solubility in water. Solubility in water because, again, water is a polar solvent. It will dissolve polar substances. So between the 4 choices, the answer here, which is going to be the most applicable to what we've been establishing here, is that carboxylic acid is... Nope, that's actually false. Wait. Okay, so you're being asked here which among the following statements is true. So letter A will go. Let's just go through all of them. Less soluble in water than alcohols. That's going to be false. Letter B, have higher boiling points than aldehydes and ketones. So you have here higher boiling points. Again, if you have a more polar functional group, it's going to result in a higher boiling point. So letter B looks like the potential correct answer here. Letter C, less polar than alcohols. That is false. Letter D, more soluble in non-polar solvents than aldehydes and ketones. So that's going to be false as well because you have non-polar solvents. Since your carboxylic acid is a functional group, it's not going to be soluble in nonpolar solvents. Okay, let's proceed. Number 2, which of the following is not a lipid? So the answer here is wax. Wax is not, by definition, a lipid. So that's just a trivial fact. I think I've mentioned that in discussion. Number 3, the double bonds in naturally occurring fatty acids are usually blank isomers. So you have letter A, a cis isomer. Letter B, trans. Letter C, both cis and trans. Letter D and E, you have essential and non-essential. So you have letter D and E, which are obvious wrong answers. So you can remove them out of the question because we're talking about isomers. So there's no such thing as essential and non-essential isomers. So we only have those isomers that we've had in our discussion, the constitutional isomers, the enantiomers, the cis and trans isomers, and especially for double bonds in particular. You have here double bonds that is going to refer to the alkene functional group. You can have two isomers, which is going to be the cis and trans isomers. So for fats and fatty acids, the naturally occurring isomer is going to be the cis isomer. Cis, wherein both of the both groups that are bonded to your double bond are on the same side. So it's going to be represented wherein if you have a double bond, it's going to be connected like so. Like this will be your carbon here, the rest would be hydrogen. Whereas if you have a trans, you have this one, the carbon connected here on the left is in the opposite side to the carbon that is connected to the right. So your H is going to be here and here. So in line structures, in line structures, you would mostly see the cis isomers introducing bends to your structure, or kinks as we've come to describe them. Whereas, on the other hand, your trans isomers are going to be more so likely going to follow the linear chain of your fatty acid, because again, it's able to maintain the what is happening here. Okay. Able to maintain the linear structure of your alkanes. But just as a trivial fact, the naturally occurring form of isomer in fatty acids is the cis isomer. We can have trans isomer in nature, but those are typically rare. Trans isomers are usually synthesized in the process that we call the hardening process. Okay, number 4, the role of very low density lipoproteins. Low density lipoproteins. So in our discussion with lipids, you have the triglycerides, the fatty acids, all of those lipids are being transported by these so-called lipoproteins from your liver to your cells, and then from your cells or tissues back to the liver. So depending on its density, we categorize the lipoproteins depending on their density. So we only concern ourselves here. Actually, there are 4, but for the majority of our discussion with lipoproteins, we have the 2, which are the 2 more prominent lipoproteins, the HDL, high density lipoprotein, and LDL. So the HDL, high density, these are the smaller ones, whereas the low density, despite the fact that it has the word low, it's actually the bigger lipoprotein. LDL carries more lipids in its structure because this one delivers lipids from your liver to your cells. And the HDL, the smaller lipoprotein, is small because it doesn't have as much lipids in its structure. These are the lipoproteins that scavenge or collect extra lipids from your cells back to your liver. So The role of very low density proteins, the most appropriate answer between the choices is going to be letter A. You have scavenging the cholesterol from cell membranes. Letter B is not applicable to your... Oh no, wait. You're being asked about lipoprotein. Sorry, my mistake. So the answer should be transporting cholesterol esters from liver to your tissue, cells or tissue. Number 5, what happens to a carboxylic acid when it is dissolved in an aqueous solution with a pH of 2? So you have here 4 choices. Letter A, it will exist only as its protonated form. Letter B, it will exist only as its deprotonated form. Letter C, it will exist as both, with the protonated form relatively in greater amount. And letter D, it will exist as both with a deprotonated form in relatively in greater amount. So remember that your carboxylic acid functional group, C double bond O OH, can undergo deprotonation. Actually, I don't have much room to write in this page, so I apologize if this seems a little bit cluttered, but I'm just going to write over the text here. So you have C double bond OOH. It's going to be deprotonated because the H here is acidic, so it can be donated out. And then your carboxylic acid becomes deprotonated. It gains a negative charge. So if you have a pH of 2, that is going to imply a high concentration of protons. Because there is a high concentration of protons, then your acid is not going to have a need to donate its OH into solution because there's already a high concentration of H. So the more predominant form in your solution is the protonated form. But there is a sort of an option here where it kind of throws you off. You have A and B that states that your protonated form or deprotonated form is going to exist exclusively. That is not going to be a correct response, because even if your pH, say at 2, although your protonated form is going to be the predominant form, does not mean that a little it doesn't necessarily mean that your deprotonated form is completely not in existence. So a little bit or a trace amount of your deprotonated form is going to exist. Again, this process is in equilibrium. This is a forward and backward reaction. So this one, majority. This one still exists, but in a very small percentage. So the correct answer here should be letter C. It will exist as both the protonated form and deprotonated form, with the protonated form existing at a relatively greater amount than your deprotonated form. Okay, number 6. The reaction when the carboxylic acid is reacted with an alcohol in the presence of an acid catalyst is called... So this process is a simple trivial fact that is going to refer to the process of esterification. Esterification, not esterification. Esterification. So you should be able to answer this one with conviction. Again, the esterification process is where you react your carboxylic acid with an alcohol, OH, to form your ester bond. So your ester bond, C double bond O C. This one. Of course, in the presence of an acid, so you have here H plus as a catalyst. Okay, number 7, what is the main difference between active transport and facilitated transport? So for this option here, you have, for the options, you have here, letter A, facilitated transport uses proteins, but active transport does not. Letter B, active transport uses ATP to power transport, but facilitated transport does not. Letter C, active transport occurs across the plasma membrane, but facilitated transport does not. Letter D, active transport moves a substance from a region of higher concentration to a region of lower concentration, whereas facilitated transport moves a substance from a region of lower concentration to a region of higher concentration. So which do you think is the most applicable definition there? So recall that you have various modes of transport across your phospholipid bilayer. You have the passive transport, that is diffusion. Diffusion is where you don't spend any energy at all. That is going to be, as the name implies, passive. That is going to occur for your species at a higher concentration, to a gradient of lower concentration. Then you have two then you have a second kind of passive transport, but it's not diffusion, it's called facilitated transport. Facilitated transport. This one is simply diffusion, but it is being facilitated by proteins across the membrane. So this one occurs again from a region of higher concentration to a region of lower concentration. Difference here is that this one uses proteins. Recall in our discussion with the lipid membrane. So if you have lipid bilayer structure, so certain proteins are embedded within the structure, and those proteins can be used, say for example, as a specialized tunnel for certain chemicals to pass through, but still it does not require any energy to transport the species of chemicals across the membrane. It's just that it's making use of a protein, kind of sort of like a special channel or a tunnel, specialized tunnel for species to pass through. And then you have the active transport that is in contrast to the passive transport, that is going to, one, make use of ATP, that's why it's called active, and also this one goes against the gradient. You have a region of low concentration to a region of high concentration, that is active transport. So with that in mind, I cannot anymore see the options. So with that in mind, which do you think is the appropriate answer for number 7? So, oh yeah, and by the way, your active transport, because it uses ATP, it also makes use of proteins. So letter A is out of the question. So both facilitated and active transport, they make use of proteins. So active transport uses ATP to power transport, but facilitated transport does not. Seems like a correct answer. Actually, I think this is the correct answer. Letter C, active transport occurs across the plasma membrane, but facilitated transport does not. So for both kinds of transport, of course, the point of transporting your chemicals is to carry the species of chemicals from the other side of the membrane, from one side of the membrane to the other side. So both of them should transport your should occur across the plasma membrane. So letter C is not a valid option. You have letter D, active transport moves a substance from a region of higher concentration to a region of lower concentration. This statement is incorrect. Again, for active transport, this is going to be a reverse of the passive transport, wherein it should be from a region of low concentration to a region of higher concentration. So letter B is indeed the correct answer for this item. Number 8. Membrane lipids in a lipid bilayer are held together primarily by A. Hydrophobic interactions, B. Covalent bonds, C. Hydrogen bonds, D. Electrostatic interactions, letter E. All of the above. So the answer here should be letter A. Hydrophobic interactions. This is going to refer back to our discussion with micelles, right? So the reason your micelles form such a structure, because this is the most stable configuration for your fatty acid structure, wherein you have the hydrophobic tails and the hydrophilic heads. So in an aqueous environment, of course, your hydrophobic tails would not want to interact with the water, so with aqueous media. So it's going to try as much as possible to hide and then have all of its hydrophilic structures, the hydrophilic heads, be exposed at the outside to interact with water, because it is the water-loving part. So similar to your lipid bilayer, they form lipids bilayer structure because all of the non-polar hydrophobic tails would want to be hidden away from the aqueous media, that is your cell and the extracellular environment, and then have all of the hydrophilic heads interact with water. So all of them are being governed by hydrophobic interactions. So you don't have any covalent bonds. A characteristic of your lipids is that they are all aggregate structures. So tipok lang na sila dinaa. They are not held together by a particular bond. There is no hydrogen bond there. If you have a hydrogen bond, that's going to pertain to functional groups like your alcohols, your carboxylic acids, and again, the ones that are holding these together are the hydrophobicity of your lipid structure. Electrostatic interactions, that's going to pertain to charges. If you have an ionic compound, positive or negative, so there are no ionic interactions here. So the answer is letter A, hydrophobic interactions. Again, that is a primary characteristic of your lipids. Number 9, the fatty acid that has higher melting temperature. You have the 4 options here with a denotion. So I've introduced to you this kind of systematic denotion for your fatty acids, that your fatty acids can be described by 2 numbers separated by a colon at the middle, and the first number indicates the number of carbon atoms within the fatty acid structure. Say for example here, letter A, 16, 0. That's going to imply that there are 16 carbon atoms in the chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that would be the fatty acid structure. And then the second number, you have 0. That's going to imply or indicate the number of double bonds that are present within the structure. So 0 would mean that there are no double bonds within the structure that is being described by letter A. Letter B have 18-0, so that's going to be a fatty acid with 18 carbon atoms and 0 double bonds. Letter C, 18, 1, so 18 carbon atoms with 1 double bond. And then you have here omega 9. So that's just going to imply where in the structure your double bond is found. So that's going to indicate that it is found at the 9th carbon position. And then letter D, 18, colon 2, so 18 carbon atoms with 2 double bonds. So for the properties of your lipids, you have here the trend that your fatty acid is going to have a higher melting temperature if it's going to be if you have a higher number of carbon atoms, or you have a longer chain, so higher carbon atoms, number of carbon atoms, so that's going to result in a higher boiling point, because you're going to maximize the interaction between chains. So the longer the chain is, the more interactions there are, and then that's going to decrease. So if that's going to decrease, the boiling point is going to decrease with the number of double bonds. So if you have a higher number of double bonds, that's going to decrease the boiling point. So for number 9, the fatty acid that has a higher melting temperature, that is going to pertain to the fatty acid that is the longest in structure. So you have here letter A and letter B. Both of them are seem to be in comparison. So letter B should have a higher melting temperature than your letter A. So letter A is out of the question. And then you have B, C, and D having the same number of carbon atoms. So the next point of comparison is going to be the number of double bonds. So you have 0, 1, and 2. So if you increase the number of double bonds within the structure, that's going to lower the boiling point. So therefore, the higher or the highest melting temperature here, or actually the property in question is melting temperature, but that is actually correlated with the boiling point. If you have a higher boiling point, that's also going to mean you have a higher melting point. And same goes with the lower boiling point, lower melting point. So here you have letter B with 0 double bonds. It's going to have the highest melting point. Again, the reason is that because you have a saturated fatty acids here, 0 double bonds, so you have a maximum stack of your fatty acid chain. They can maximize the London dispersion forces. Plus, there are no kinks in the structure, so they can stack neatly on top of each other. They can be more of a solid structure, therefore it's going to melt at a higher temperature. In comparison to, let's say for letter C, if you're going to introduce at least 1 double bond, then it's going to kink out. The structure is going to kink out, and it's going to introduce a disorder to your structure. It's going to be more liquid. Then you have a lower melting point if you increase the number of double bonds. So the correct answer here is letter B. Okay, next. Number 10. Arrange the carboxylic acid derivatives in order of resistance to hydrolysis. So you have 3 carboxylic acid derivatives that have been introduced to you, namely the anhydrides. You have the esters, and then you have the amides. So between the 3, you have the amides as the most resistant to hydrolysis, being the more or the most stable bond out of the 3. Next would be your esters. They are somewhat stable. There are strong bonds, but they can be easily hydrolyzed via the addition of an acid or a base catalyst. And then you have the least stable out of all, which is the anhydrides. They can be easily hydrolyzed, or actually they are readily hydrolyzed with the addition of water. So in order of resistance to hydrolysis, this should be the answer here, which is letter B, this one. Okay, number 11. Choose the structure that is typical in trans fatty acid. So trans fatty acid, that is going to be characterized with a double bond wherein the carbons that are to the left, to the right are on the same side. We can take a look at all the three structures. Letter A, this is the double bond here. This part here, so the carbon to the left and to the right is that looks weird. Okay, so you have this one, the carbon to the left and carbon to the right. So both of them are at the bottom, so the same side, so this is a cis. The second double bond, you have also the same case, so both of the double bonds here are in cis configuration. Letter B, we have here, this is the double bond, so the carbon to the left is here on top, the carbon to the right is here at the bottom, so this is actually a trans isomer. So letter B seems like a correct answer, but just for the sake of verification, we'll take a look at letter C. Letter C, you have here the carbon to the right here on top, to the left, to the left, this one is on top, this one is also on top, so this is also a cis configuration. So you also have here a third carbon which is to the left, which is also at the bottom. You can make a case that, hey, kani siya nasa ubos, kani nasa taas. So they should be on the opposite side, right? But again, we'll take into account that there is this one which is on the same side as this one. So this is actually more of a cis. Can be considered a cis. Actually is considered a cis configuration. So letter B is your best answer. Number 12, cholesterol is used as which of the following? So this one is asking for the function of cholesterol in your body. Letter A, it is a component of plasma membrane. Letter B, a starting material for synthesis of bile salts. So letter C, a starting material for the synthesis of other steroids. And letter D, all of the above. So the answer here should be quite obvious. Hopefully, it should be letter D. So all of the three that have been stated are uses of your cholesterol. Letter B and C, these are true because cholesterol is the precursor to your bile salts, your hormones, and not all hormones, but your testosterone and your estradiols, your female and male sex hormones, and then for other steroids as well. And then it is also a component of it is a component of plasma membrane. So you have your plasma membrane here. So one characteristic of your plasma membrane is that it is fluid in nature, but your cells doesn't necessarily have to have all of its entire surface area have a fluid structure. So it also needs for certain areas of its cell to be rigid. So what your body can actually do is insert cholesterol within the structure of your phospholipid bilayer to introduce rigidity to the structure of your membrane. So it is also a component of the plasma membrane. So letter A is also a function of your cholesterol. So the answer here should be letter D, all of the above. Number 13, the correct reaction that happens during hydrogenation of a vegetable oil. So hydrogenation, that's going to pertain to the reaction of your alkene C double bond C plus H2, that is going to be with a metal catalyst. So this typical reaction is considered an addition reaction, wherein what you do is simply add Let's choose a different color. So what you typically do is, as the name implies, addition reaction. You add atoms to your alkene double bond. So here the chemical or reagent that is being added is H2 hydrogen. So you just simply add H to both sides of the carbon, and then you lose one of the bonds in the process. The final product here that is going to be expected for this kind of reaction is going to be an alkane, so a single bond, C single bond C, and then you have the addition of your H to your original reactant. So this would be the final expected product. So let's just go over the 4 options here and spot where among the 4 has this reaction depicted. So letter A doesn't seem to be the case because you are not starting with a double bond. So letter A is already not correct. Letter B, you have this one. You're starting with an alkene, double bond C, and then at the end you obtain an alkane, and then you have the addition. Oh, actually the added hydrogens are at the bottom because the hydrogens at the of the reactant are placed at the top. So this one is the addition products. So this one, the letter B seems like a correct answer. This one. Then letter C, this one is involving a ketone, C double bond O, becoming an alcohol. So that is wrong. And then letter D, you have this one, which is simply the isomerization of this double bond. Your alkene is actually being transferred to this part of your molecule. So letter D is not the correct answer. So your correct answer here is letter B. Okay, number 14. Ooh, still have a long way to go. Number 14. Which kind of eicosanoids is thought to promote certain aspects of the inflammatory response? You have A, leukotrienes, B, prostaglandins, C, thromboxanes, D, steroids, E, fatty acids. So for this answer, the correct answer is, steroids is out of the question, and fatty acids and prostaglandins, so those are more of a hormones. Fatty acid is a component of your lipids. So yeah, you actually just have 2 possible answers here: your thromboxanes and your leukotrienes. So the correct answer here should be, this is a little bit of a trivial question, so the answer here should be thromboxanes. Number 15, which of the following pairs would yield a polyamide? So polyamide, that is a polymer of your amide carboxylic acid derivative. So for your polymers, especially for your carboxylic acid derivatives, you can only get a polymer if your 2 starting materials are difunctional polymers, difunctional. So for example, for your amide carboxylic acid derivative, that's going to require the reaction of your carboxylic acid plus an amine, NH2R. So you should have one reactant, which is a carboxylic acid, and a second reactant, which is an amine. And again, for your polymer to form, you need a reactant which is difunctional in nature, meaning to say that for your carboxylic acid, that should be a dicarboxylic acid, a dioic. So I'm just going to draw a squiggly line just to, because I'm just emphasizing here that your one of your reactants should have two functional groups. So this one here, and then your amine should be similarly the same. So H2N and then NH2. So two functional groups. So we have A, B, C, and D. So you just simply take a look at the the combination here that's going to depict a dicarboxylic acid and a diamine. So the correct answer here should be letter A, this one, because you have here, this is a dicarboxylic acid and a diamine. So this is going to give you your polyamide. Letter B is not a dicarboxylic acid. This one is an alcohol, although this one is a diamine, but this one is not a dicarboxylic acid. Your letter C is a dicarboxylic acid, but this is a diol, a difunctional alcohol. So this is not going to give you a polyamide. This is going to give you a polyester, because the reaction of your carboxylic acid with an alcohol is going to give you an ester. The polymer of an ester is polyester. So letter C, although it will give you a polymer, it's not going to give you a polyamide. Letter D is wrong, because this is not a difunctional carboxylic acid. So your correct answer is letter A. Number 16, when solutes cross a cell membrane from a region of lower concentration to one of higher concentration, the process is referred to as... Should be able to answer this one. This is basically the definition of your diffusion. So the transport of your materials from a region of high... oh, wait, sorry. Okay, that was actually a trick. Pay attention to the terminologies used. You have from a region of lower concentration to a region of higher concentration. That is actually the opposite of diffusion. So that is going to be the opposite of diffusion, which is active transport. If you're going to go against the gradient from low to high, so active transport. So osmosis is simply your diffusion, but this is going to refer specifically to the transfer of your water from a lower concentration to a higher water of higher concentration to an area of lower concentration. This is going to be movement of water, but still the same idea for your diffusion, high to low. Facilitated diffusion, as I've mentioned in the previous question, is going to be the same with diffusion, but the difference is that for this one, this involves the use of your transport proteins that are embedded in your plasma membrane. Letter D, electrophoresis. I don't think I've discussed electrophoresis, but seems like a wrong answer. So letter E is correct. Active transport. Number 17. Fats are blank and oils are blank at room temperature because greater portion of fats are blank fatty acids while oils are blank fatty acids. So this is a question that requires you to fill in the blanks to make a correct statement. So this one, just simply try to match the terms that are given to you in the four choices. So fats are blank and oils are blank. This gives you a consequence, a reasoning, because a greater portions of fats are blank and oils are blank acids. So you have A, solid and liquid. So you can insert here either solid or liquid. So by definition, your fats are called fats because these are your triglycerides that are solid. So fats are simply your triglycerides that are solid. So solid triglycerides. So here should be solid. And then by definition, your oils are called oils because these are the liquid form of your triglycerides. So both of them are actually triglycerides. They just differ in the phase they are in. So oil is liquid. So letter C and D seems to be out of the question. And then at room temperature, so room temperature, because a greater portion of fats are blank, so saturated or unsaturated. So fats are solid. This is going to refer back to our structure of your fatty acids, that if you have a long chain of fatty acids, especially if they are saturated, they're going to stack more neatly, they maximize their interaction, so on and so forth. They form a more solid structure. Again, because they have a greater portion that are saturated. So saturated. And then oils, because of the introduction of cis double bonds that are going to be kinky in nature. They cannot order themselves properly. So they're not going to result in a more solid. They have a more fluid structure. So oils have, most of them are unsaturated in composition. So the correct answer should be here. The first one is saturated and then unsaturated. So letter A should be the correct answer here. Number 18, which is the major function of triglycerides? You have letter A, components of your cells, B, source of energy, C, transport, D, communication. So your triglycerides in your body, they can actually have a number of functions, but your triglycerides are mainly used as sources of energy. This one, triglycerides. So fats and oils, so they are more of a storage, energy storage, forms of stored energy. So the major components of your cell membrane, they are not triglycerides, those are phospholipids. So you have the triglycerides, wherein you have this one, you have a glycerol backbone, glycerol, and then you have 3 fatty acid chains, so triglyceride. And then you have the phospholipid, which has the same glycerol backbone, but the difference is that it has only 2 fatty acid chains. The third one is being occupied by a phosphate group. So this is the one that is actually the major component in your cell membrane. Letter C and D seems like not an option for your triglycerides. Again, they are mostly used as energy. More correctly speaking, energy storage. Because in our body, what we make use for our major source of energy is not triglycerides, but carbohydrates in the form of your glucose molecule. Okay, for numbers 19 to 23, you are asked to match the molecule below with the class to which it belongs to. So you have here 5 classes. You have cholesterol, phospholipids, sphingolipids, triglycerides, and unsaturated fatty acid. And then you're given here this, and this structure. So you have 5 structures also. So number 19, you have cholesterol. So if you see a tetracyclic structure, then it's going to hint that it's maybe perhaps cholesterol. And out of the 5 structures, you have this one that is going to be cholesterol. So this is in fact the structure of your cholesterol. So I believe I asked you to memorize at least the structure of your cholesterol. Number 20, let's change the color of our pen. You have phospholipids. So phospholipids is going to be your lipids that are going to contain phosphate group. So among all of here, let's try to see. You have letter D, this one. This is a phosphate group. So this is a phospholipid. And then, but wait, there's more. You have letter E. Kindly take a look at this part of the molecule. This is also a phosphate group. Letter E is also a phospholipid. So you actually have two applicable molecules for number 20. Number 21, you have sphingolipids. Sphingolipids is going to be your lipid with the sphingosine group. It's going to pertain to letter E. This part of the molecule is your sphingosine, and then you have the phosphate group attached at the third, not the third, but actually at the supposedly third carbon. If you're going to compare that one to the glycerol counterpart. Then number 22, your triglycerides. So triglyceride is going to pertain to the lipid that has a glycerol structure, and then you have 3 ester bonds with your 3 fatty acid chains. So your triglyceride is going to look like your letter A. So this part of the molecule is your glycerol. You have this 3, which is the ester bonds. Then this one is your 3 fatty acid chains. So letter A is your triglyceride. Letter D is not a triglyceride because although this part of the molecule is glycerol, and then you have this one, which can be a fatty acid, but this part of the molecule is not a fatty acid. So letter D is actually not a triglyceride. That also goes for letter E because again this is a sphingosine, doesn't have the glycerol backbone. Number 23, you have unsaturated fatty acid. So fatty acid, you have the long chain. Oops. Let's make use of a different color just for giggles. Don't have any other color. So long chain fatty acids, this one. So you have C double bond OH, and then you have a long alkane or alkene chain. And then you have the presence of double bonds within the linear chain. So that is your unsaturated fatty acids. Okay, moving on. Number 24. Which steroid is responsible for both the successful initiation and completion of pregnancy? This one should be relatively easy to answer. The answer would be here. Your progesterone, which is part of your female sex hormones, along with estradiol, which is going to initiate and also signal the completion of pregnancy. Number 25, what will be the product when 4-hydroxybutanoic acid is heated with H2SO4 or sulfuric acid? So 4-hydroxybutanoic acid. So you're given there a name. So actually for this answer, you are being expected to draw the structure for you to actually get a hint as to what reaction will occur. So 4-hydroxybutanoic acid, that is 4 carbon atoms, 1, 2, 3, 4. Oic acid, going to suggest a carboxylic acid group. 4-hydroxybutanoic, so 1, 2, 2, 3, 4. So you have the OH here. Actually, I'm going to draw the OH like so because this is going to be more convenient later on. And then this is going to be heated in the presence of H2SO4. So H2SO4 here is just going to be an acid catalyst. So look at your molecule. You have here a molecule that is that contains two functional groups within its structure. You have one, a carboxylic acid, the second one being your alcohol, and if you could remember, there is a certain reaction that involves a carboxylic acid and an alcohol, especially in the presence of an acid catalyst, that is your esterification process. So what would happen here is that your your hydroxyl group is going to internally react with itself. This is going to form a ring because, again, it reacts with itself, and usually for those kinds of molecules, it forms a ring. And a ring, which is ester in nature, and we call cyclic esters lactones. So this one, letter C. So the correct answer is letter C. Lactones, by definitions, are your cyclic esters. So letter A, polymer, is not the correct answer. Letter B, anhydride, is not going to be correct. And letter D is not correct. For this one, you're going to expect a reaction. Number 26. Aspirin reduces inflammation and fever by inhibiting the formation of which of the following types of messenger lipids? So you have letter A, thromboxanes, B, progestins, C, prostaglandins, D, leukotrienes. The answer here is going to be your leukotrienes. Number 27. The effect of partial hydrogenation of a fat or oil is which of the following? So partial hydrogenation. So in the hydrogenation of fats, say for example, if you have a fatty acid, so if it contains a double bond, it's going to most likely be a cis double bond. If you're going to subject this fatty acid in hydrogenation, H2, let's put here metal catalyst, as it usually is the case, it's going to result in a, I don't have any more room, I'm so sorry. Okay, so it's going to give you a saturated fatty acid at the end. So it will give you a linear structure. But you can also have a partial hydrogenation. Partial hydrogenation, so that's going to happen if you have I'm lost in thought. Okay, so partial hydrogenation, same process, but you're actually limiting the reactants of your hydrogen. So for the partial hydrogenation process, you actually, instead of giving a saturated fatty acid at the end, you're actually converting your cis double bond to a trans double bond. So you're getting a linear structure at the end still, but you're obtaining but you're still not completely getting rid of the double bond or the alkene at the end of the process. So that is what happens during a partial hydrogenation. So among the four choices, you have which here? Which of the following is going to be the correct answer? So this is going to decrease the degree of unsaturation. Nope, that is actually wrong because you're not getting rid of the double bond at the end. So letter A is wrong. B, decrease in the melting point of the fat or oil. So decrease in the melting point of fat or oil, that is also wrong, because what happens is that you come from a form which is kinky in nature, that is actually this one, Again, no stacking, no order. So it's going to have a low melting point. And at the end, you have a linear structure, although it has a double bond. So, but because it's linear in nature, it can stack properly. So it actually increase the melting point. So letter B is wrong. Letter C, increase in the number of fatty acid residues present in a molecule. You're not going to increase the number of residues. So that is also wrong. Or D, the melting point and fatty acid unsaturation remain the same. This does not also make sense. Melting point and fatty acid unsaturation remain the same. So letter D seems to imply that nothing happens. So that's not also correct. Oh wait, I got it mixed up. Oh no, I'm correct. So this one, the kinky form, you have low melting point because this is liquid in nature. And this one is high melting point because this one is linear in nature. Actually, for number 27, there doesn't seem to be a correct answer here. So, yeah. So for number 27, there doesn't seem to be a correct answer. Okay. So, but I think here the answer should be letter B. But I think instead of decrease, the operative word there should be increase. I think we got this one mixed up. Okay. We're just humans. Okay, let's proceed. Number 28. An oxidation product of cholesterol. So this one pertains to your bile salts. Bile salts. So the structure of your bile salts, actually in our discussion, that's going to be the first definition of your bile salts. These are oxidation products of your cholesterol. In their structure, recall that the structure of your bile salts contains those hydroxyl groups that are actually found on the same side of your tetracyclic structure. So that's what gives it its non-polar polar regions, which make it a good emulsifying agent for your fats. Okay, so bile salts. Okay, number 29, another name for your phosphatidylcholine, that is going to be letter A, lecithin. So the addition of the choline, a molecule, to your phospholipid. So letter A, lecithin. Number 30, what will be the product when propanamide is reacted with ammonia? So this one, propanamide, you're given a name, so you're kind of expected to draw the structure in order to get an idea as to what is going to happen for the reaction. So propanamide, so that's going to be 3 carbon atoms. 1, 2, 3. Oops. I drew too many. 1, 2, 3. Yeah, I was correct. So this one, propanamide. 1, 2, 3. 3 carbon atoms. Oh wait, that is propanamide. That's an amide. Not propanamine. So wait. 1, 2, 3. This one is amine. This one is propanamide. So amide. C double bond O, NH2. Okay. And then it's reacted with ammonia. So let's draw this one a little more to the left. 1, 2, 3. NH2 plus NH3. So what will be the product when propanamide is reacted with ammonia? So the amide functional group especially is a very stable bond already. Actually, if you've noticed all of the reactions from your carboxylic acid derivatives, all of them, the final form is your amides. So your anhydrides, they can be converted to amides. Your esters, they can be converted to amides. but your amides, they don't want to be converted to other carboxylic acids, and they don't actually react at all. They are only able to undergo hydrolysis reactions. So with ammonia, actually no reaction is going to occur. So the correct answer for number 30 is no reaction. Okay, so let's proceed with the next part of the exam, which is part 2. Number 1, you're asked here to draw a simple cartoon / diagram to represent a portion of a lipid bilayer membrane. Label the hydrophobic and hydrophilic portion of the membrane, its prominent features and structures. So I'm not going to force myself to draw when I can show you just how your phospholipid bilayer should look like according to the fluid mosaic model. So your membrane should look like this one, wherein the prominent features are, you have here the phospholipids, you have the hydrophilic, this is your hydrophilic heads that are all oriented in the outward position, interacting with the water, which is going to be the expected environment of your cell, inside and outside. And then you have here the hydrophobic tails that are hidden away within the, why did I write hydrophilic? Hydrophobic tails that are hidden away or hidden inside the phospholipid bilayer structure. So not only that, you're being asked to label the prominent features and structures within your phospholipid membrane. So you have here, like this one, this is a transport protein that is going to participate in facilitated diffusion as well as active transport. So some of them are embedded across the entirety of the phospholipid. Some of them are embedded just partially. Some of them are decorated inside. Some of them are decorated outside. And then some of them are actually carbohydrates that serve as markers. Some of them function in communication as well as marking your cells. Recall our discussion with the blood typing. So your carbohydrates determine the properties of your cells. So these are the prominent features. Of course, I'll be looking into how you drew the phospholipid membrane. I will actually appreciate if you actually emphasize the fluid nature of your phospholipid by drawing it like this way. It's a little bit fluid, wavy. So although in most of our depictions because I'm drawing this one relatively quickly, so mostly I'm just able to draw a linear manner of representation, but more accurately it should be like this one. Okay, so maybe I'll give incentives for those who drew, but I'm not going to take away points for those who actually just draw it linearly like this one. Okay. Number 2. In a dietary context, you're being asked what is the difference between good cholesterol and bad cholesterol, and how do HDL and LDL differ in function. So this one pertains to the lipoproteins. It's a little bit of a misnomer because bad cholesterol and good cholesterol does not really pertain to cholesterol in itself. It's actually referring to the lipoprotein, which is a protein, only describing as to what these proteins are actually being or doing or functioning as. So you have various kinds of lipoproteins. The two most prominent is the HDL and LDL. And then you have between the two, let's just you have the, oops, you have the H, okay. You have the HDL and LDL. I think I've discussed this one in the earlier portion of this video. So your HDL are your high density lipoprotein. These are the smaller lipoproteins, and the LDL are the larger of the lipoproteins. Your HDL has low lipid concentration, and then your LDL has the higher lipid concentration because it's larger. It contains more lipids, so that includes your fatty acids, your triglycerides, and your cholesterol. Your LDL functions to deliver your lipids from your liver to your cells and tissue, and your HDL collects, operative word there is collects, and scavenges excess, that's also an operative keyword there, excess cholesterol and lipids from your cells back to your liver. So in a dietary context, you have the HDL labeled as the good cholesterol, the good kind of lipoprotein. Why? Because these are the ones that collect, again, excess lipoproteins, excess cholesterols and lipids back to your liver, wherein it can manage those cholesterol for other functions of your cholesterol. Whereas your LDL is labeled as the bad kind of cholesterol, because these are the ones that distribute your lipids to your cells, and also because they are the ones that contain the highest amount of lipid concentration, which can leak out in your what do you call this one? Your blood vessels, and then it can form plaques and then increase your risk of cardiovascular diseases. And again, by nature, your HDL by function, they scavenge and collect the excess lipids back to your liver. So in dietary context, it's labeled as the good kind. Your LDL is labeled as the bad kind of cholesterol. Again, it's a misnomer. Cholesterol there's no such thing as a good and bad cholesterol. It's just there is a difference in function between the proteins that transport these cholesterols around your body. Okay, I hope that makes I hope you were able to follow that kind of logic, reasoning, and was able to explain that one in good grammatically correct English in your paper. I'm sorry, this video has gone way too long. I'm speaking too much. I'm already stuttering. Okay, number 3. This one's fun, hopefully. Number 3, complete the reaction by filling in the structure of the missing reactant or product. So you have here multiple pathways. We can take a look at the center, which is considered the starting point for all of this one. This is a carboxylic acid, specifically 1, 2, 3, 4. So 4 carbon atoms. That is going to be called butanoic acid. And then let's follow this path here first. This one, if you take this path, you're being asked, why is it not erasing? Okay, so for this path here, going to the right, you have here a reactant B that's going to react with your butanoic acid to give you this product. So notice that this product is, you have this one, C double bond O, C double bond O. That is characteristically your anhydride. So for your anhydride to form, you need to react a carboxylic acid with another carboxylic acid. So how do you get the other parent carboxylic acid? So you can just simply take a look at this structure. You break this bond here, I think we've done similar reactions in previous videos. You put an H here, you put an H here. So this one, 1, 2, 3, 4. This is your butanoic acid, this one. And then you have this one, 1, 2, 3, 4. That is actually another butanoic acid. So you just simply put here a second butanoic acid as a reactant. This one will give you your anhydride. Okay. Next, coming from your anhydride, you're being asked what reactant is necessary to form product G, which is named butanamide. So you're already given there the name butanamide, so you should be able to draw the structure of the product letter G. So butanamide, that's 4 carbon atoms, 1, 2, 3, 4. So double bond O, and then it's an amide, so C double bond O NH2. How do you get an amide coming from your anhydride? So your anhydrides can be reacted with an amine or ammonia, specifically NH3, to give you your amide, because what happens, your NH3, this one attacks the carboxylic carbonyl group here, this one breaks, so you get here, and then it's going to abstract this H here, so you're going to get a second product, which is actually your carboxylic acid. So there's 2 products here, but you're only being asked one, which is butanamide. So the reactant that is needed to get your butanamide is NH3 or ammonia. Oh, how come I can't erase this one? Oh, okay. Okay, so let's follow this track here, which is your butanoic acid reacted with ammonia. What will be the product of that one? So NH3, same thing happens, will form a bond with your carbonyl carbon. Your OH will go away. It's going to abstract one H here to form water. This one is going to give you, hey, look at that, they're just the same. So butanamide, so another butanamide. So letter E is also butanamide. What is going on? I can't anymore erase my writings. Okay. Next, let's follow the reaction going here. So for this reaction, you're being given already the other reactant that is going to be reacted with your butanoic acid to form product A. So the other reactant here, this one is an alcohol in the presence of an acid, which is likely acting as a catalyst. So this one, you have a carboxylic acid and an alcohol, so that is typically your esterification reaction. So in your esterification reaction, this OH here is going to form a bond here. This one, the OH here goes away, abstract the H here to form water. So you will get 1, 2, 3, 1, 2, 3, 4. C double bond O, O. This one is 1, 2, 3, 4. So you typically have 1, 2, 3, 4. 1, 2, 3, 4. So this would be your ester. Oops. Let's try to draw that one a little bit neater. So 1, 2, 3, 4. C double bond O, O, 1, 2, 3, 4. 1, 2, 3, 4. Okay, so that should be the correct structure of your resulting ester product. Now, from this ester, you're being asked what would be reacted to this ester product to give you product C and D, which is butanoic acid, one of which so butanoic acid is one of the reactant, and question mark. So in order for you to recover your original butanoic acid, because again your parent here is butanoic acid, so this is butanoic acid. So how do you recover your original parent molecule? So usually that involves the reaction of hydrolysis. So you add water, so you're essentially breaking this apart again. You put an OH here, you introduce your H back. Actually, simply just the reverse of the esterification process. So you get butanoic acid. So the structure here should be butanoic acid, OH, and this one, which is the reacting molecule, which is 1, 2, 3, 4, your butanol. So 1, 2, 3, 4. Butanol. So you have this one, the other product, which is butanol. So in this case, you're simply just reversing the process that you did. That you did here. You're just simply reversing the process. So this part here is simply the reverse of this part here, and the reverse of that is just the hydrolysis of your esterification. So I apologize if this is a little bit cluttered in presentation. It's very difficult for me to draw on the screen, but hopefully this is this explanation is clear. Okay. Okay, lastly, you have number 4. In number 4, you're being asked to draw the structure of a triglyceride using the information that is given below. So you have letter A, all the fatty acids have 18 carbon atoms in their chain. Letter B, the second fatty acid is unsaturated at its 9th carbon atom. Letter C, this triglyceride has undergone partial hardening or hydrogenation. So triglyceride, automatically you should draw the glycerol backbone. So CH2, CH2, CH2. You have the ester bond. So C double bond O, C double bond O, C double bond O. So this would be the typical backbone of your triglyceride. What only differs is in structure is the fatty acids, the long chain fatty acids here that is going to comprise your triglyceride. And for this particular question, it describes that all the fatty acids have 18 carbon atoms in their chain. So let's try to draw. This is 1. So the carbon here, the carbonyl carbon is considered the first carbon, 1. So this one is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, that looks perfect. Okay. So for all 3, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That looks good. Okay, letter B, the second fatty acid. So the middle one, this one here. Oops, what happens? What happened? So the second fatty acid is unsaturated at its 9th carbon atom, meaning to say that there is a double bond at carbon number 9. So let's try to look for carbon number 9. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there should be a double bond here. Now for your double bonds, the naturally occurring double bond is a cis double bond. So typically you should have a kink here a bend, but hold your horses. Letter C, the triglyceride has undergone, so this particular triglyceride overall has undergone, so undergone, has undergone, meaning to say that it's already finished undergoing partial hardening or hydrogenation. And as I've mentioned earlier in this video, that during the partial hardening process, you don't really lose the unsaturation. Instead, you convert the cis to a trans configuration. Did I just burp? Sorry. Please excuse me. So this one, so you just simply draw this one as is, as a linear trans configuration. So this would be how your triglyceride for number 4 should look like. Fairly easy. Okay, so I think that's the end of the exam. This video has gone quite a lot. Yeah, it's a long video, sorry. But hopefully this was useful to you. I'm still planning to give out more videos like this one, especially for the other topics that we have yet to discuss on nucleic acids. So yeah, please watch out for that one. Thank you very much for watching. See you again in the next video. Bye!